Hi ChemExcel, here's our energy diagrams video 1. Energy diagrams are like little puzzles with 3 points and 2 equations. So let's get in this video, we're going to see how to interpret an energy diagram. So using the 3 points and 2 equations to help define the 5 variables and identifying a reaction as exothermic or endothermic, which is review. And then how to apply the 3 points and 2 equations to construct an energy diagram if you are given 3 of the 5 variables. So a couple of things we know so far. Right? We've already seen the endothermic versus exothermic. So we know that this diagram here is endothermic. Right? We can see that from start to finish, energy was absorbed. And we know that this diagram is exothermic. From start to finish, energy was released. Right? We also know how to define that start and finish. We have reactants over here, products, reactants, products, right? Those always go in the same places. Right? And the new stuff we're going to talk about in this video deals with this activation energy here, okay, which you have already seen a little bit about in the collision theory videos. And we're also going to be defining what's going on at the peaks of each of these hills. All right, so 3 points, 2 equations. All right, the 3 points of the graph are the reactants, the products, and that new one, the peak, is called the activated complex, abbreviated as AC. The activated complex is made when the reactant bonds have broken, but new bonds haven't formed yet, all right? Or you can think of it as just this weird transition state, all right? It's an unstable state. It's not a reactant. It's not a product. It's not really a proper molecule, okay? This little diagram over here shows 2 HI molecules and a transition state here where these bonds right here would be in the process of breaking. This is kind of in the process of forming a new one. Nothing's really fully done there, okay? It's not a proper molecule. All right, the 2 equations that we have are for change in enthalpy. We've seen delta H values before, all right? When we've done stoichiometry, we had delta H values going along with each balanced reaction, all right, that identified exo and endothermic. And it's always going to be P minus R, all right? And then we also have activation energy, all right, which you've already seen again in the collision theory video. It's how much energy is needed to break the bonds, and it's going to be AC minus R. So those are 2 really, really important equations. They never ever change, all right? They are what they are, all right? If you need to add anything to your notes at this point, that summary sheet, please feel free to do so, and just pause the video anytime you want to add something onto that summary sheet. All right, we're going to use these 2 energy diagrams just to kind of locate all 5 values and state what they are. So we know that we always start with reactants, right? That on there. We always end with products, so those points are very easy to locate. And the peak of the hill is always going to be the activated complex. So starting off, defining those is pretty straightforward. In this case, we would say R is 80 kilojoules, right? Because that's where R is. We have the AC is at 280 kilojoules, and P, right, or sorry, 240 going across there. Let's change that. Okay, 240, and P right there across at 160. On our other diagram, we have R is at 350, AC is at 450, right, 350, 450, and P is at 200. Okay. All right, get rid of those lines now. All right, we need all 5 values on here though, so we still need to do the activation energy, and yes, it is E with a little subscript of A. That is the correct variable. Please use it. And we need to locate the delta H on here as well. All right, in the next video, you're going to see why the activation energy is really important to a unit about reaction rates. Okay, so that's going to be something to just pay attention to exactly where it is on here. All right, if we want to show that the EA is AC minus R, all right, then we're going to have to kind of block off where that is. So we have an arrow going between AC and R. I've just kind of dotted line, extended that out here. I'm going to label that activation energy. Do the same thing over here. All right, so extend R out and take that difference between AC and R, label it EA. So in this case, all right, we have 240 minus 80. It's going to give us 160 kilojoules, I hope. And then EA over here, okay, if we're doing AC minus R, then we have 450 minus 350, right? 450 minus 350 right here. Let's give us an activation energy of 100 kilojoules. Right? Delta H we know is P minus R. Okay, so we want to show the difference between P and R. So I'll just keep extending R out here. That'll be the easiest way to do that on this one. So the difference between P and R can be delta H. All right, over here, there's a couple different ways you could do that. You could draw your delta H here. All right, if you don't like that, if you like to put your delta H always towards the end, all right, you could extend this out over here. All right, you could even put that in here. Doesn't really matter. Any of those things are still going to show you that the delta H is going between R's value and P's value. Okay, so on our first graph, we have 160 minus 80, right? P is 160, R is 80. That's going to give us 80. And on the other graph, delta H is going to be P minus R. I'm emphasizing that here because you notice P is lower than the R. Okay, so that's going to be 200 minus 350. Gives us that negative 150. So delta H is the only value that can be negative on here, and that's because it's a change value, right? Delta means change in. Changes can be positive or negative. None of these other variables up here have that delta in front. This one does, so it can be positive or negative. That's why doing P minus R, right, is going to be super, super important for calculating that delta H. It's not just bigger number minus smaller number. All right, in terms of making an energy diagram, all right, you can see that in this problem, we've been given 3 of those 5 variables. We have the products at 150, reactants at 400, activated complex at 450. This one's a really straightforward graph. Okay, so if we put products at 150, all right, reactants at 400, put that up here, activated complex at 450. Okay, so products at 150, as it says, reactants are at 400, activated complex, it says at 450. All right, and then once I've placed all my points, I can go ahead and I can connect them. All right, it does say label all 5 variables. That's only 3 of them. So remember my activation energy. Squeeze in there. It's pretty small in this case, but it's between AC and R. Right? You can also think of it as the height of the upward hill. Okay, if you go from left to right, you have to go up this hill. It's how tall that hill is. Right, and then I'll put my delta H on here. It's got to be the difference between P and R. Okay, so we've labeled all 5 variables there. You can also see that this graph is exothermic because our delta H would be negative. Right, we have this one, P minus R. It's going to give us 150 minus 400. Throw some units in there. Squeeze them in. Going to give us negative 250 kilojoules, right? Exothermic reaction, right? Energy dropped. Is it likely to be fast or slow? Okay, that's a question that we're going to answer in the next video. And we're going to see in the next video really how it relates to this hill that I talked about. Okay, this one's going to be a faster reaction, right, due to that small hill. All right, but we'll delve more into that in the next video. All right, I just got more energy. energy diagram here, just showing when you're not just given each of the 3 points, how you get those 3 points, okay? So in this one, we're given the products at 200. It says the activation energy is 400 and the change in enthalpy is 150. So products, right, that's P. Activation energy, that's E sub A. That is not the peak of the hill. That's important. Activation energy and activated complex sound similar, and some people read this and just put the peak of the hill at 400. That's not what it says. You have to do what the problem says. Right? Change in enthalpy, that's our delta H value. So you can see we've only been given one of the actual points on this graph. So if I start trying to draw it, all right, I can say, well, put 200 about here. I can put the products there, but I can't immediately place any of my other points. Okay? So that's where those two equations come in handy. All right, activation energy is AC minus R. That doesn't seem helpful at the moment because I don't know either of those. So this is not a useful equation yet. And we have delta H is P minus R. Oops. All right, that is useful right now because I've been given the delta H value. I've been given the P value. All right, and I can solve that for R. So I'll let you think about that for a moment. Okay, we get R equals 50 kilojoules. So we'll put 50 down here. Okay, and then we can just confirm that. Like this is a endothermic reaction. It has a positive delta H value. So we should see it go up from start to finish, and that is what we have here. All right, now that we know R, we have enough information to use this first equation. We have the activation energy is 400 kilojoules. We don't have a value for AC, but now we have one for R, which is 50. Yeah. So solving for that, we're going to get our activated complex being at 450. So we're going to put that peak of our hill up here at 450. And I'm trying to keep my spacing at least in some sort of logic, okay? You know, I'm not going to make you put every increments of every 100 on there, but I don't want to see like 200 right next to 450 with this huge gap between 50 or something. 200, that doesn't make sense. Okay. Then I'm going to connect my points. All right, and if you kind of think back to that last slide where I said that would be a fast reaction, we can think this one looks like it's going to be slow. That's a pretty big hill. So you got a little preview there. That's a big hill. That's more likely to be a slow reaction. All right, labeling those last couple of things. We do need to label all 5 of our variables. That's a requirement. Okay, we're going to show our activation energy, and we can see clearly here it is 400. It's going between 450 and 50, right? And then our delta H, right? We can see that that matches with that 150. It's going between 50 up to 200. Okay, all right, so that's your intro to energy diagrams. You can either go ahead and do the next video and get all the notes sort of today and do the practice tomorrow, or if you want to stop at this point and just do the parts of the energy diagram practice that you can, sort of ignoring the questions that maybe you can't answer, especially anything to do with a catalyst, all right, then you can go work on the parts you can do and then watch the rest of it tomorrow and then finish up then.